Okay, so let's now use Gauss's law to find the electric field produced by the infinitely long line of charge. So here's our infinitely long line, and we made some plus signs indicating a positive distribution of charge, and I think we call the charge density lambda. So we have lambda as the charge density. And we want to apply Gauss's law to this. So what does Gauss's law say? Well, it says that the integral of the electric field over a closed surface is equal to the charge inside of that closed surface divided by a number, epsilon naught. So, as we mentioned before, if we want to use Gauss's law to find E, we need to find a closed surface on which the electric field is everywhere the same, so that we can pull E out of the integral and end up with an expression that looks like that, where we no longer have a vector expression because we've evaluated the dot product. Okay, so that should then look like that. And so we have to think about the charge distribution and the symmetry of the electric field. So if we look at this from a perspective like that, so sort of the charge comes right at us, then so here is the line of charge, and at some distance r from that line, the electric field has some value, and it must have the same magnitude everywhere at the same distance r. So if we go, if the infinite line is the center, the drawing isn't great here, but the infinitely long line of charge goes through the center of this imaginary circle of radius r. Doesn't matter what that radius is, as long as this is at the center of any circle. On those circles, the electric field must have the same value everywhere. Of course, on different circles, the electric field can have different values, but once we pick a circle of radius r, then the electric field there has the same value. So we end up sorry, it's not actually a circle. That's part of a surface that has that includes this line. Right? We need a closed surface, and so from this perspective, we can tell that along that line, the electric field will everywhere be the same. That has to be part of our two-dimensional closed surface. So basically, what we're saying is that if the radius is r, so if we look at it from this perspective, and the radius is r, then what seems to us like a circle is really a cylinder. Well, we can make it as long as we want. So a cylinder, there's nothing special about. Let's see, make the charge continue a little bit further. So we have a cylinder there. On the surface of the cylinder, that's where the electric field's everywhere the same, but we also have to close off the ends. But the ends don't really matter. They make the surface closed, so there are two disks at the ends, right here, we're looking at it from this perspective, because the electric field, if we draw the electric field in red, from this perspective, on this surface, the electric field is pointing straight away, right? It's pointing like that, and on the bottom part, the electric field is also pointing away. So the electric field goes straight through the part that is cylindrical, but it doesn't go through. We don't have any contribution to this integral from the endpoints, because the electric field here. So we can assume we might assume that the electric field is stronger here, and pointing away down here, but it's not going through the surface there. And so when we do the dot product, so let's just sort of be complete here. We have the dAs, which are normal to the surface. The dAs here are pointing in the same direction as the electric field. Right, so I'll make a few dAs. These are normal to the surface. And here they're pointing that way. So we get a full contribution, E dot dA here. All the electric field goes through the surface, so to speak. But here, the dA is pointing this way, right? So the dA and the electric field E, which is drawn in red, on the sides, don't give any contribution to E dot dA, right? Because they're perpendicular to each other. Same is true over here. The dA is pointing that way, and so the electric field, the red electric field, so maybe we can label some of these as E, doesn't produce any electric flux, right? So the integral of the electric field over a surface is defined as the electric flux, and we get no electric flux contribution from the sides. So it's only the cylindrical part that gives us some contribution, and so we integrate over the cylindrical part, and we get that the left-hand side looks like E times the area of that cylinder. Well, we can imagine opening up the cylinder, and it's basically a rectangle. It's a rectangle where this side is, if we look at it from this perspective, it's the circumference, which is 2 pi r. So this side is 2 pi r, and this side we have to choose. Let's just call it L, however long we made it. And so we get that whatever the electric field is, times 2 pi RL, that's the left-hand side of Gauss's law. And on the right-hand side, we have to look and see how much charge is inside. Well, the charge that we care about is all this charge. That's all that. That's the charge that's inside of our closed surface. How much charge is that? Well, Q enclosed is the charge density lambda times the length. So that's lambda times L. And so Q enclosed over epsilon naught looks like that. And so from that, we can then solve for the magnitude of the electric field, which is lambda over 2 pi epsilon naught r, and turn that back into a vector by adding a unit vector, which is, this is sort of, it's not a radial unit vector, but it's radial in every plane, so it's radial in cylindrical coordinates. I think that's the way to say it. Okay, so if we look at it from, if we look at the electric field from this perspective on the surface, then we have what looks like a radial electric field, but we have no components that are sideways, right? So it's not actually a radial electric field. And in each plane, it's radial. Okay, so compare this to what we had. I think we had the variable y when we solved for it using the brute force approach, but we get the same thing in one line using Gauss's law. And we'll apply this technique to find other configurations of charge where there's symmetry such that we can pull out the electric field like that.